Today we're going to go on a journey together. It's the journey through the history of recommendation algorithms that I myself went through when I started to work at Outbrain. I'll attempt to present this journey in 15 minutes. I'll start with some basic background on what are recommender systems, and then I'll present three algorithms: Logistic Regression, Poly2 and Factorization Machines. And finally, I'll present one of the cutting-edge classical algorithms called Field Aware Factorization Machines, or in short, FFM, and show why it beats them all. Hi, I'm Schwartz. I'm a data scientist in Outbrain. I develop machine learning infrastructure, as well as research, develop, and deploy machine learning models, and I love trekking high in snowy mountains. Netflix, Spotify, Outbrain. What do all these companies have in common? They all have recommender systems. Netflix recommends music or TV series they think the user will want to watch. Spotify recommends music they think the user will want to hear. And Outbrain recommends content they think the user will want to read. Very generally, the common question to all recommender systems is, how likely is the user to click on the ad? As a hiker, I really like looking into hiking gear. So let's look at some backpack ads as an example. In the table attached, you can see 4 ads as an example for backpacks. 3 of the first columns, publisher, advertiser, and volume, are descriptions of description information, and we call them features. The 4th column is called clicks or non-clicks, and we use it to calculate click-through rate, or in short, Ctr. So what is Ctr? Ctr is a common metric we use in recommendations, which calculates the number of users who clicked on the suggestion, divided by the total number of users who viewed the suggestion. So for example, in the first row, we have 90 clicks and 10 non-clicks, so all in all, 100 views, so we get a Ctr of 0.9. Without going into the optimization of the algorithm, the aim is simple. The algorithm will learn the historical ads and their CTRs, so it could predict the most accurate predicted CTR. Why? So that the recommended items could be ranked based on their predicted CTR. Let's say I want to suggest the ad I think will interest the users the most. In theory, I would like to publish the ad with the highest predicted CTR. Now let's deep dive and see how it's done. So the first algorithm I want to present is logistic regression. Logistic regression is the most commonly used algorithm in the classification world. It classifies an event if it's true or false. In our case, if a user clicked on an ad or not. If the probability of the user who clicked on an ad is above 50%, we will classify it as if there was a click. If it's lower than 50%, we will classify it as if there wasn't a click. This equation models the relationship between a feature and the predicted CTR. I'll simplify it a bit, but we can see we have a W multiplied by X. So the X here is the feature. What is the W? W is the weight or significance of the feature. The higher the weight, the more significant the feature is in predicting the CTR. Let's look at the example. We now have a weight of Yao multiplied by Yao, a weight of Deuter multiplied by Deuter, and a weight of 50 liters multiplied by 50 liters. But let's look a little bit more on the first line. We can see that Deuter, when publishes in Yao, has a CTR of 0.9. But when Deuter publishes an MSN, there's a CTR of 0.05. So there's a relationship here between advertiser and publisher, and we would like to model it well in our algorithm. But when I have an individual weight for each of the features, this relationship won't be modeled. So if to sum up logistic regression, it's simple, convenient to explain, and easy to scale, but it only represents linear interactions. So if we want to model something nonlinear, we have to manual feature engineer it ourselves. And this brings me to our second algorithm called Poly2. Poly2 has the same linear equation as in logistic regression, but now it has a nonlinear term as well. Again, I'll simplify this equation, but what we see here is a combination of all feature pairs, and every feature pair has its own weight, so it's a weight of both features. And again, I'll show it in an example to make it clearer. So now we have a weight of Yao Deutel, plus a weight of Yao 50 liters, plus a weight of Deutel 50 liters. So now that we have this weight of Yao Deutel, this resolves the issue from the logistic regression. I could have concluded this talk here. So what's still the problem? The problem is how Poly2 addresses new data points, data examples, or data that is very few. Let's look at the example. We can see here we have low alpine. Low alpine wasn't appearing in the data train, and because of that, we didn't have a weight for it. So now a weight will be formed, but it's the first time this weight has been formed, so it's not very accurate, right? And it won't give me the accurate predicted CTR I'm looking for. So if to sum up Poly2, it's simple, convenient to explain, and easy to scale, but it gives trivial predictions for unseen data and unreliable predictions for interactions that are very few. But I have to stop here. I kind of stretched the truth a little bit. And this table doesn't really look like in real life. So how does it look like? A little bit more like this. You can see I still have publisher, advertiser, and volume, but now it's embedded, which means there's no more categorical data. Now it appears as zeros and ones. One represents if the feature exists, and 0 represents if it doesn't. I'll explain a little bit more in factorization machines. So I want to present the third algorithm, factorization machine, or in short, FM, which uses vector interactions. So as you can see, I still have the linear term of the logistic regression, but now I have another term and it's represented by vectors. And what do I mean by that? If we look back at our metrics, we now create a vector of publisher, a vector of advertiser, and a vector of volume. And we dot productize these combinations. Let's look at the example to make it clearer. We have a vector of Yao with the dot product of a vector of Deutel, a vector of Yao dot product of vector of 50 liters, and a vector of Deutel with a dot product of vector of 50 liters. So before I want to stop here and say why this factorization machines help us against the problem we had in Poly2. And it's because the way we have the embedding of the vectors. So because we have embedded vectors, we now have all the information of the entire dataset, which includes the low alpine that we encountered in the Poly2. And because of that, it will give a better prediction compared to Poly2. So what's still the problem? Let's look at the vector Deutel. The vector Deutel is used for the vector Deutel is used in two different interactions, with the interaction of Yao and interaction with the vector of 50 liters. So if I use the same vector to represent two different interactions, I'm still a little bit missing the point here. I won't get the accuracy I'm looking for. And this brings me to my final model, but not before I summarize this one. So factorization machines handle sparse datasets, but it uses the same feature vector to represent all interactions. So now let's go to our cutting edge algorithm called Field Aware Factorization Machines, or in short, FFM. Before I explain what does FFM do, let's talk terminologies. So up to this point, we called publisher, advertiser, and volume features. Now let's change the naming. So publisher, advertiser, and volume will now be called fields, and their categorical information, such as Yao, MSN, Deutel, Osprey, Low Alpine, 50 liters, 62, etc., these will be called our features. So why these terminologies? Let's go to the equation and we'll see the diff. So we can see that in the upper equation, we had our equation of the FM, and then we had a vector combination. But FFM uses a vector with its corresponding field to make the predicted CTR much more accurate. And let's look at the example to make it clearer. So there's now a vector of Yao with the corresponding field advertiser, with the dot product of vector of Deuter with the corresponding field publisher. Then we add a vector of Deuter with the corresponding field volume, with the dot product of a vector of 50 liters with the corresponding field advertiser, and a vector of 50 liters with the corresponding field publisher, dot productized with the vector of Yao with the corresponding field of volume. So if we go back to the problem we had with FM on Deutel, we now see that we have a different vector of Deutel represented in the interactions. So with the interaction with Yao, I have a vector of Deutel publisher, while with the interaction with 50 liters, I have a vector of Deutel volume. So now that each interaction is using a different vector, it will give me this advantage compared to factorization machines. So I want to conclude. FFM is amazing, and the only disadvantage I could have thought about is it's represented only in two-dimensional interactions. So we're going towards the end of this journey, and I know it's been a dense and a quick journey, but I want to sum up again what we saw throughout our journey. So we started with logistic regression, but it only showed linear interactions and didn't give us the extra mile. Then we moved on to Poly2, which gave us non-linear interactions, but still it didn't perform well when encountering new data examples or data that doesn't appear much. Then we moved to factorization machines, which work well with sparse data sets. But there we encountered a problem when we had the same vector representation in a few interactions, which brought us pretty close to the predicted CTR of our accuracy, but still not quite there. And because of that, we moved on to FFM, which is a bit advancement of factorization machines, which used the corresponding fields for each of the features, and that gave us the extra mile and the predicted CTR we want. Thank you very much for listening, and I'd be happy to answer any of your questions if you have any.